Okay, now for the third and final part of chapter 20. Now we're going to talk about a statistical view of entropy, or what is in grad school, or maybe even you could even do an intro course to it, like a senior year in a physics program. It's called statistical mechanics. Statistical mechanics is an application of statistical methods at the fundamental or to the fundamental interactions at the molecular level in order to explain bulk properties of matter. So you take what happens between two molecules in a gas and use statistics and the physics of that interaction to describe what's happening overall in the bulk matter of the gas. So one of the things that comes out of this is a different way of looking at this problem of, hey, we've got 4 molecules of gas here and 2 there, or 3 here and 3 there. And one of the big questions that comes in is, what are all the possible states we can be in, right? What is our multiplicity? So how many different ways can we be in this state? Because you got to remember, this molecule could be here and this one there. So there are tons of ways that we can do this, and it comes down to the multiplicity of the configuration is n factorial over n1, the number over here, factorial, and n2, the number over here, right? And we assume all microstates are equally probable. Well, if we start looking at that, what we find is that the number of states for even something like n is 100 molecules, right? And we look at the extreme, all right, at the very extreme where all of them have drifted over here and we essentially have none over there. Well, in that extreme, there's only one state for that, right? And there's only one state for that because all of them are over here. It doesn't matter if you're swapping them out with each other, they're still all over here, so there's just one state for that. Well, even with just 100 particles, when you go to, well, what if it's 50-50? And half are on this side, half are on this side. Well, at 50-50, the possible number of states is 1 times 10 to the 29, right? So, while there is a finite probability to get all the molecules in the room over on 1/2 of the room, that is so small compared to what's going on around the average, which is you got half on one side and half on the other. Boltzmann came up with his entropy equation, which is the total entropy is K, the Boltzmann constant, times the log of the multiplicity, right? And here K is a Boltzmann constant. Stirling has an approximation for log n factorial. This just has log n factorial in it, right? If we go back and apply that to our free expansion problem before, we started off with initial state, Wi is n factorial of n factorial 0 factorial, which is 1. So the entropy of that state, right, was 0. And then if we look at, all right, so what's our final multiplicity, where half the molecules are on one side, half are on the other side, we can break that down. We can use Stirling's approximation to log n factorial. And what we actually end up with in the end is the entropy is the number of molecules times the Boltzmann constant times the log of 2. And since capital N, number of molecules, equals K, times K is number of moles times R, we can also write this as NR log 2. And that is our little bitty peek into statistical mechanics. All right, that's it for chapter 20.